Hi, good day everyone. My name is Kevin Sanka and this is my quick demo of the ENVISAT project for MECH5108. So I just want to start off with the main function. So Cartesian trajectory generation. We see we generate two trajectories, one from the home to the extended and then from the extended to the capture position. This is kind of what that function will look like, just basic stuff for the cubic time scaling. The next aspect we're going to look at is the inverse kinematics, and basically what this would do is convert these trajectories into joint positions. This uses the Newton-Raphson method, and basically it computes the error on the space vector twist and updates the joint angles accordingly with the Penrose inverse of the Jacobian. It also makes use of the forward kinematics as well. And then we just compute the joint velocities and accelerations and then stream that data to Simulink. In Simulink itself, we see the data we're streaming in, and we have the PD control here, which is just the computer torque control function, and it uses the dynamics as well to compute the updated torques. We also see some displays, and then this is the robot model here, which is the same as in the report, and the ENVISAT model here. So what we're going to do now is get into the simulation itself and what we would be expecting to see while we simulate would be these graphs update live. So if I click play, the robot should go from the home position as you saw there and the graphs reset to the first position we marked was the extended position. This is basically just allowing the robot to get to a pose that it could then reach any other poses in the workspace. So we also see that the robot arm, in terms of modeling, we model the launch adapter ring as just a hollow cylinder for now, as it's typically at the back of the ENVISAT spacecraft, and we don't want to fill the simulation space with a lot of objects that don't actually have an interaction. It typically stays in this pose for around 10 seconds, and then it would go to from the extended pose to the capture pose, which is currently doing. And nice. So we can stop the simulation there, and we can basically see from the simulation that the position is correct. However, the orientation still leaves some to be desired off of. Doing a further analysis of looking at the graphs, we can see that the reference position and actual positions on the left hand side for all the joints, and then the reference and actual velocities on the right hand side. So in terms of the graphs, we see that the first three joints track pretty well with what we wanted, but the last three joints did not, and we see some steady state errors occurring in these joints. This is could be solved by adjusting the PD controller gains. In terms of velocities, however, we see that the velocities all track pretty well, except for some variations in the fourth and fifth joints. But coming down towards the end, all the velocities did go to zero. So the PD controller, in terms of oscillations, is able to damp the system, and the system would be considered stable. So with that, that's the end of my presentation, and thank you for listening.